Hello, and welcome to another video in this series as we learn the basics of lean for writing maths proofs. Today's quite an exciting video today because we're going to be looking at another interesting kind of proof. Generally the proofs we've been looking at have been more or less straightforward, and we've done that necessarily because we're learning from scratch, but also to get familiar with the contents of a lean proof. In this sort of second phase, we're going to be looking at proofs that have a little bit more structure. So today we're going to be looking at proof by cases. Broadly, the idea is that we divide a task into smaller tasks, I guess, and if we can prove each of those individual pieces leads to the same desired result, then we've kind of proved it overall. That's sort of speaking wishy-washy plain English, but you'll see the specifics in this video. So let's look at a given task. This is deliberately kept as simple as possible, and like a lot of the proofs that we've looked at, we start off with a given fact, a hypothesis, something that is given to be true, and we want to work out, derive, prove a result. So we're given this thing. So in the past we might have seen hypotheses, given facts, that say something like A is 4 or X is 3. This looks a little bit more complicated, so we'll talk a little about what that is. What this is saying is that X is 3 or X is minus 3. So this symbol here is used in logic. It's a logical or. It means either one of those two things or both could be true. Another way to think about it is at least one is true. So it's never the case that none are true. It's always the case that one or more are true. So either this is true, and in some cases both things can be true, not always. But for this task we don't know which, and our aim is to prove that x squared is 9. Now, because these proofs are really, these kind of maths challenges that we've chosen are really simple, we can do a lot of them in our head. So we know that if x is 3, x squared is 9, so that kind of makes sense. It puts us at ease. X is minus 3, x squared is again 9, so we know we're not dealing with anything particularly unusual. But we're going to look at how we would do this in slightly more detailed steps. In our minds we know this is true, but we're going to try and write out a proof in small enough steps that are translatable into a lean proof. So this is the slides which I'll put online, so you can read them in your own time. So that symbol means logical or, and the statement something or something, P or Q, in our case x equals 3 or x is minus 3. P or Q means either P is true or Q is true, or possibly even both. And those kinds of statements are called disjunctions. That's just a fancy way of saying or, A or B, P or Q. Yes, there exists other logical connectors like AND. So P and Q would mean P and Q are both true. P or Q means P is true or Q is true or both. And in some ways the OR case is more interesting. The AND case is simpler in some sense. So if you think about the previous videos that we've done, we might have had more than one hypothesis, H1 and H2, and they're all true. So in some sense H1 and H2 are true. So that's almost a simpler case. So that's why we kind of start with this OR case, because it's more interesting. It's perhaps more difficult. So that's just introducing a fancy word, disjunctions. And just if you're interested, the AND case is called a conjunction. So P and Q is a conjunction, P or Q is a disjunction. So we want to show x squared is 9 follows from that hypothesis. Again, that's a statement of the obvious, but I'm working through this step by step so that we can break it into the pieces which we can then reconstruct in Lean code. So that's why it might seem laborious or obvious, but the thing we're trying to learn is how to break a maths problem down into pieces which we can then reconstruct as a Lean proof. So it's worth kind of training our brains to do this, and we've done it now for quite a few videos, 6 videos in fact already. So the hypothesis tells us that x is 3 is true, or x is minus 3 is true. So those are two cases. We don't know which. We don't know if this is true and that's false, or we don't know if that's false and that's true, or which way around it is. And in some scenarios both can be true. You might have x is 3 or y is 5, and those potentially both could be true. In this specific case we know that both can't be true because x can't be 3 and minus 3. So these are two cases. So let's kind of think a little bit about how we would prove that. Well, we want to show that whenever the hypothesis is fulfilled, the conclusion is true. And that means there are two scenarios in which the hypothesis could be true. X is 3 or x is minus 3. Those are the two scenarios in which the hypothesis overall is true. And those are the two scenarios we're going to test. We can test. And those become the two cases. And it's just a picture that kind of visually shows our starting point on the left hand side, which is x is 3 or x is minus 3 as a hypothesis, a disjunction, and we want to prove that x squared is 9. And what we've done is we're going to break the more complicated hypothesis into two simpler ones. X is 3 we're going to test, and test that x squared is 9, and we're going to test x is minus 3 and make sure that becomes x squared is 9. That leads to it as well. Why these two cases? And this is really important actually, so it might sound obvious, but it is important. There's two things we need to think about here. One is that these cases are what make the hypothesis true. Second thing to think about is to make sure that we have enough cases to make sure that we've not left out any scenario in which the hypothesis is true. So let me draw a picture there just to explain that. So normally we would say we're given a hypothesis and we want to prove using algebra or other things, other methods, taking steps to a conclusion to prove that. So that leads to that. Now if the hypothesis is more complicated, perhaps it's a disjunction. Let's have a disjunction of three things: P, Q, R. So the hypothesis says P or Q or R are true. Any one of those could be true. Any multiple of them, as in P could be true, Q could be true, R could be false. At least one and possibly all could be true. Now what we're going to do is split that into three cases. Well, imagine if we only split it into two, P, Q, and we tried to prove that that leads to the conclusion, and that leads to the conclusion. So let's think about those two things we talked about. Number one, we're testing the cases, case 1, case 2, case 1, case 2. We're testing the cases that make the hypothesis true. That's true, that we got that. But the second point we said was we have enough cases so that we've not left any scenario out which makes the hypothesis true. And in this case we're not testing, we forgot about case 3. Because if case 3 is true, if R is true, then the hypothesis is true. And if we didn't test that, then we haven't got got a complete proof. So we need to make sure that we do test all the cases that make the hypothesis true. So that was a question mark there because we left out case 3. So it's not enough to just split and take pieces of the hypothesis. We have to make sure that we cover all eventualities that make the hypothesis true. So those are the 2 things to think about when you're doing a split. So in this case, it was relatively simple. It splits into 2, but just for future, that's worth thinking about. So let's write down the steps. Again, this may seem laborious. It may seem that we're writing down the obvious, but this is training our brains to break down a problem and write it in such a way that the translation to lean is not that difficult. So we always start by writing out the given fact, the hypotheses. It's always a good habit. So we've written that down here. X is 3 or x is minus 3. It's a disjunction. That's our given fact. And that's all we're given. From this, we are creating almost 2 intermediate results. Remember the last video, we created intermediate results. We're creating kind of 2 cases. And I'm going to use the word case because that's the proper terminology for splitting something like this and then having to test all of them. So we have 2 cases, and the first case is x equals 3. How do we know that? How do we justify that? It's from the given fact. It's from the disjunction. So it's using fact 1. I'm going to label this 2. Now we want to prove something about x squared, and we say, well, what could it be? Well, we know that in this case, x is 3, so it's 3 squared. So using the case, using this intermediate fact, but it's actually a case. And then that's 9. So we've proven it for the first case. We have another case remaining. We're saying the second case is x equals minus 3. How do we know that? We're using, again, referring back to the given fact, which was a disjunction. So using fact 1, and we're going to call this 3. And again, we're having to prove something about x squared. This time x is minus 3, so it's minus 3 squared, which is 9. So in both cases, we've proven that x squared is 9. Let's rephrase that. In both cases, we've proven that the conclusion x squared is 9 is the same. Both cases lead to that. That's what we wanted to do. And just to check, are there any other cases? Is there a third option? Is there a third case? No, there isn't. These 2 cases completely cover the possible scenarios in which the hypothesis could be true. There's no other case in which this is true. So that's important to just always check. So we've proven that whether x is 3 or x is minus 3, x squared is always 9. This is just writing out some of what I've said. If you wanted to go through that in slower time, you can pause the video and read it yourselves. There's also a blog which I'll link to. So in the blog, I choose my words a lot more carefully. When I'm on this video, I just talk off the top of my head. So if you're kind of unsure about a point, have a look at the blog, because the blog is written with a lot more thought and care. So let's look at a lean proof. And what we'll do is, because there's some new things in here, we'll start with looking at what's familiar, because the overall structure is exactly the same as what we've worked with over the last 6 videos. We've got the usual comment at the top, we've got the import of the tactics. We start with example, because we're not naming this theorem. We declare our variable, so x is an integer. We're saying that there is a hypothesis. This is where the hypothesis goes. And this time, well, we recognize that it's called h. And then we have a statement of the hypothesis. And this time, it's a disjunction. So the new thing here is this use of v as the symbol for logical OR. You can type \or in most lean editors, and it will turn it into the correct symbol, but v will work. And And then we've got the thing we want to prove, the overall proof objective. And that's no different from what we've seen before. X squared is 9 here. And then we're entering into the proof. So we have to justify this given the hypotheses. And then we've got a proof. Now this looks a little bit more interesting now. We have seen calc before, but we've not seen obtain before. So we're going to talk about that. But given that we've talked already about the maths idea behind proving this, you can guess what this does. It takes the hypothesis and splits it into two cases, and they become the intermediate results in some sense, or the intermediate temporary hypotheses, HA and HB. So you can guess what they would be. HA will be x is 3, and HB will be x is minus 3, and we'll use those one after another as the two cases to prove that x squared is 9, and that's what happens. So we've got an entire section here, there, that's first case. Then straight after that we've got the second case, and you can see they're both calculations, because proving x squared is 9 is just a simple calculation. So calc we've seen lots of times before, and it's saying we're about to do a calculation, and we're about to calculate what x squared is, and we're saying we're justifying that it's 3 squared by using the rewrite tactic. We've seen that many times already, using HA, the hypothesis, the temporary one that's relevant to the first case. So let's actually just look at the live kind of editor to see and check that we understand what HA and HB are. So let's have a look at what Lean thinks is happening. So if I put my cursor at the end of the first line, that the Infoview will tell us what Lean thinks is happening. It tells us that Lean knows that x is an integer there. It knows that there's a hypothesis that x is 3 or x is minus 3, and it's using that symbol. And it knows that the proof objective, the goal, is x squared is 9. That's at this point. Then we run the obtain, which, as we said, splits the disjunction into two cases and calls the smaller hypotheses HA and HB. And we can see here what those are now, because we're putting our cursor at the end of that line, so that's been executed. So we're saying that you can see the two cases here, two goals. The first case, and it's even using the word case to describe them. So in the first case, which is just this thing here, x is an integer, and this time the hypothesis is no longer h, but x equals 3, and we have to prove x squared is 9. And you can see that's easy, and our calculation does that. So HA is what we referred to when we justified x squared is 3 squared. HA is x is 3, so we can do that. And then that's 9 by using just normal arithmetic. And then we just have one more case to do. And this time the case, if I put my cursor there, bit fiddly. This time the remaining case, there's only one goal left now to prove, which is the second case where x is minus 3, and we have to prove x squared is 9. Again, really simple, and that's the HB is now the hypothesis for the second case. So x squared is minus 3 squared, justified by the rewrite rule referring to HB, which is that temporary hypothesis relevant to the second case, and it's 9 by using normal arithmetic. So it's really helpful to kind of use the Infoview to see what's going on now that we're beyond the very, very simplest proofs, and it's sometimes the goal, the proof goal changes. So overall the proof goal was x squared is 9 given that hypothesis, but now in the proof by cases we're working with interim temporary hypotheses. Let's draw a picture just to kind of clarify that. So we might have had a hypothesis that said P is true or Q is true. And when we do obtain, and we say H1 vertical symbol, H2 referring to H3. Have I got that syntax right? Let me check. Yeah. What that does, it splits H, which is P or Q, into two temporary hypotheses, P and Q. And they exist just in the context of proving those cases one after another. And when they're proven, they're gone, and we're back to the overall proof goal. Because remember, these are not true in general. P is not true in general. P or Q is true in general, but we're looking at this case specifically, then this case, and hoping that they both lead to the same conclusion, the desired conclusion. So that's what obtain does. It splits a disjunctive hypothesis into the two pieces. So just to illustrate that, in case that isn't completely clear, if that was x equals 3 and that was x equals minus 3, then H1 would become x equals 3 and H2 would become x equals minus 3, and that's what we had in our code. So there you can see x is 3 for this one and x is minus 3 for that case. And then when we put our cursor outside, then, well, in this case there's nothing else now because the proof itself is done. So that's what this, you can see how this now relates back to the maths proof that we did. We split the hypothesis into cases, and then one after another we prove them. Now you might say, well, how do we know which way round it was? Was it x equals minus 3 first? It's always, well, I think it's left to right, but you don't have to kind of assume that. You can check by putting your Infoview on, putting the cursor in the after obtain, and then you can see the kind of the cases, and in the sections, in the calc sections, you can see which one is the current case. So here the current case is x equals 3, not x equals minus 3. So that's a useful skill actually, to be able to just check which part of the proof, or which way around the proof or the subproofs that you're kind of working on, just by checking in the Infoview. Now you might have noticed these dots. So those are good style. What they do is two things. Number one, it's a visual clue that this overall proof has been split, has two subproofs, which is this one here and then this one here, and there's an indent you can see, but the dots kind of demarcate those, and at a glance you can see that from the overall proof there are two subproofs involved. So that's one benefit. And the second one is that it restricts the Infoview, once you'll kind of put your cursor inside there, within the context of a dot, a focusing dot they're called. The Infoview is restricted to showing information just relevant to the kind of the subproof. Great. So that's what those dots are. They're called focusing dots. So just to summarize, the hypothesis is a disjunction. That letter V denotes logical OR. Let's talk briefly about typing that thing. So I'm just typing some scratch here. I could type V, or I could type slash and then OR, and then press space, and it will turn it into the symbol for V. And that also works for other things like AND, which is the upside down version of that, or even capital R for turning it into the symbol for reals, or /Z. So there's a few of these shortcuts. Sometimes you can't easily type some of these symbols, so the backslash is greater than, for example, or less than or equal to, oops, did I get that right? Less than or equal to, or greater than, or you can just use that, for example. So that's just a little handy tip for typing these proofs. So obtain splits a disjunctive hypothesis into smaller pieces, and they become temporary hypotheses related to the two cases, and we have to prove them one after another. The Infoview is really helpful for showing which of the cases we're kind of currently trying to prove, and the calc sections are just as before. And we talked about the focusing dot, so it's visually useful to kind of see at a glance what the structural proof is and where the subproofs are, and it also restricts information in the Infoview to the current goal, to the current subproof, and that's really helpful as well. So if we place the cursor before obtain, let's do that. If we place the cursor before obtain hasn't been run, so our hypothesis is that disjunction. That's kind of what we expect. So that's what we would see. If we place the cursor after obtain, that means the hypothesis has been split into two. So let's do that. And we saw that earlier, we're just rerunning it for practice. We can see now there are two hypotheses, HA and HB, with the two cases. And then if we place our cursor inside one of those subproofs, say inside here, you can just see the information relevant to that. So x is 3 for this one, and x is -3 for that one. Brilliant. So that was actually, I think, really interesting for me, because this kind of proof was not just a direct kind of derivation. It needed some interesting things to be done with the hypothesis and splitting into cases. So I would say this is the first really meaty, interesting type of proof structure that we've learned about how to write in Lean. As always, we finish with a really, what we call an easy exercise. They're easy because the maths is not hard, and the idea is to just practice what we've learnt in terms of the code, just by kind of changing it a bit, but the idea is to practice it. So if you can do this, then you've kind of grasped the main kind of ideas. So the idea is to prove x squared minus 3x plus 2 is 0. Don't worry about how complicated that looks. We're just plugging in values, and when we do the calculation is 0. So the proofs will have a calc just like the one we've done. So you could start with the code for our example proof and then change it to do this exercise. Here x is real, so not an integer. Although for this particular problem I don't think it matters too much. And we're given a disjunctive hypothesis that x is 1 or x is 2. Now in our heads we can plug x is 1 in, so 1 minus 3 plus 2 is 0, and we can test this one as well. 2 squared is 4 minus 6 plus 2 is 0. But that's just reassuring. But the idea is to split this hypothesis using obtain into two smaller hypotheses which are relevant to the two cases we need to prove, and then do that calculation that we've just done by talking about it. So it should not be difficult at all. Any problems, comment in the replies to the video and we'll kind of discuss it. But hopefully that shouldn't cause any problems. And once you've done it, you can have the confidence that you've learnt. You can learn the main ideas. So it's just a hint and tip there, which is to create the two cases just as we did with our example with x is 3 and x is -3. So I hope that was interesting. We'll see you next time for more. Bye.